Hey there, welcome to today's lesson on electron configuration. The question of the day is how many electrons fit in each of the 7 principal energy levels? You should be able to figure this out using the periodic table and your knowledge from drawing Bohr models. You may remember the diagonal rule back from when we spoke about electron excitation in the atomic theory unit. The diagonal rule is a great trick to remember how electrons fill from lowest to highest energy. Remember, they don't necessarily fill in numerical order, but when we have really big elements, the electron configuration becomes such a pain in the neck. So our diagonal rule, remember, looks like this. We start up high at 1s2, cross through that, and then move to 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. See what happens there. We do 4 before 3. That's why we're talking energy. It fills from lowest to highest energy, even though that doesn't match the numerical order. That's because S is a little less energetic than D. And then we can continue through this for any element, really. So just a reminder, the big number out front tells you the principal energy level, which is going to correspond to the period on the periodic table. Unless you have the D shift. If you're in the D block, it's not technically the period number. It's one less than the period number. The little number up top tells you the number of electrons in that particular sublevel and in those orbitals. The maximum is listed in the diagonal rule, but you can fill less than the maximum. And then in the S orbital, we can hold a max of 2, P a max of 6, D 10, and F 14. Again, you may remember that this corresponds to the periodic table. The skinny tower on the periodic table is called the S block, and it's 2 elements wide. With our 2, we have the P block, which is the fat tower on the right side, and that is 6 elements wide. The D block is where you'll find the transition metals, 10 elements wide. And then finally, the F block should be 14 wide. Now, you very simply just fill in the electron configuration for these elements just following the diagonal rule. So the first example that we have is sodium, meaning we need to fill 11 electrons using the diagonal rule. So we would run through 1s2 would be 2 electrons, 2s2 is another 2, 2p6 brings us to 10, and then 3s1 is going to finish off sodium. See if you can do argon. Here are the answers for sodium and argon. Remember, we are just running through the diagonal rule. Sodium ends on 3s1, meaning that there is a lone electron in the 3s orbital. It has an ability to hold up to 2 electrons, but we didn't need 2 electrons, so we just put 1 in there. Argon, on the other hand, is a noble gas, so it is going to fill out the p orbital going all the way to 3p6. Argon has 8 valence electrons, which is the sum of this 2 and this 6. When we have very big elements, this diagonal rule and writing the electron configuration can become crazy big. So a lot of the time what we'll do is we will pick the closest noble gas with a lower atomic number, and then we will write that element's symbol in brackets, and then just continue the electron configuration from there. For example, in the case of sodium, we would, instead of writing 1s2, 2s2, 2p6, 3s1, we would write neon and put it in brackets because that is the closest noble gas with a lower atomic number than sodium. So we would put Ne in brackets and then 3s1, and that would be it. Now, something to note is that all of the noble gases are going to end on a blank P6. So helium is, well, helium's an exception. Helium is 1s2. Neon would be 2p6. Argon is 3p6. Krypton is 4p6. Xenon is 5p6. Radon is 6p6. This is true because each of them excluding helium. They're in the p block, so they're all going to have p electrons, and they are each the sixth in that section. So that is how we can determine that the noble gas is a p6. It's in the p block, and it's the sixth one in the p block. So it's kind of like a shortcut. So we can do that for any of these elements. You, again, are going to find the noble gas that is the closest, but with a lower atomic number. Write its symbol in brackets, and then make a mental note that it is a blank P6. And then continue from there in the diagonal rule. So arsenic has the atomic number 33, and argon is a noble gas that is the closest, but with a lower atomic number. It has 18 electrons, and it is going to end on 3p6. You could run through the diagonal rule to check on that. Just add up all of the small exponent numbers until you get to 18. Argon will end on 3p6. So you just write argon in brackets and continue from there. Running through the diagonal rule, after 3p6 comes 4s2, then 3d10, and then arsenic will be 4p3 because we don't need the full 6 to get to the 33 electrons. Additionally, arsenic is in the p block. It is in the fourth period, and it is the third in the p block. You have gallium, germanium, and then arsenic. So it's the third in the p block, hence 4p3. The same is true here for cesium and for tungsten. Again, you are going to find the noble gas that is the closest with a lower atomic number and pick up the electron configuration from there. Now, the converse is true as well, and a lot of students think that this is actually easier. You would go from xenon, which here is number 54, and then you just add 2 electrons, and you can find out what element you're working with. See if you can do that for each of these elements. Xenon 6s2 is going to represent the element barium, who has 56 electrons in total. And then krypton 5s2, 4d10, 5p2 is going to be tin, whose symbol is Sn. The reason I love electron configuration so much is because if you really know how to read the periodic table, you can kind of hack it by using an element's coordinates on the periodic table. The large number represents the period on the periodic table, which is the principal energy level. There's kind of an exception to that. It's that D and F shift, but for the S and P elements, it's very straightforward. The block on the periodic table tells you its sublevel. So if we are in the S block, then our valence electron is going to be an S electron. P block is going to be a valence P electron, and you can kind of figure that out. Then, like I was saying, if you count how deep an element is into that block, you will get the superscript, or how many electrons fit in that final energy level, in that final sublevel. So again, this over here represents the S block. P is this block, although helium really should be over here with the S because it is an S electron. But on our periodic table, of course, it is going to fit in with the noble gases. If we organize the periodic table by electron configuration, helium would definitely be over here. There are periodic tables that are printed that way, but it's not our standard periodic table. Then we have the D block, which, reminder, 10 elements wide because you can fit 10 d electrons. And then finally, the F block across the bottom. So this is what I mean by hacking the periodic table. If we look at 3p4 as the valence electron, or the 4 outermost electrons, the last entry in the diagonal rule configuration, this is going to correspond to sulfur. And I know this because sulfur is in the third period, indicated by this 3 here. It is going to be in the P block, and it is the 4th element in the P block. We have 1, 2, 3, and 4. So I know I'm going to end on a 3p4, and then you just run through the diagonal rule until you get to 3p4. Now, I have mentioned this quite a bit, and it is the D shift. Orbitals don't fill in numerical order. They fill in order of lowest to highest energy. That's the Aufbau principle. The D block period number does not correspond to the valence energy level. It's actually 1 less. So copper is right here, and it's actually in the 4th period of the periodic table. Its highest numerical level is 4, but its valence electrons won't be in 4, it'll be in 3D, because all of these electrons in this row go into 4s before they go into 3D. That is because 4s is a little bit more stable than the 3D. So in terms of the hacking of the periodic table, you would have to remember about the D shift, that the period is going to be one more than the final electron configuration, or that the configuration is one less than the period number. It's off by 1. So this is actually 3D, 4D, 5D, and 6D. Copper's valence electrons are truly in its 3rd energy level because it does a little bit of electron rearranging for some added stability. Now, there are some special rearrangements that the transition metals can make, and in this case, I am not talking about the chromium or copper specific rearrangements. So this is if you follow the diagonal rule exactly for copper. This is not the common reorganization that we see for copper. Just in case your teacher is a teacher who wants you to know the copper chromium exceptions, I am not speaking about that here. There is also an F shift, and the F shift is going to happen twice for an F block element. So truthfully, this F section of the periodic table should fit right here behind lanthanum and actinium, and titanium and everything below it should shift out to the right to make room for the F block to fit in there. So cerium or lanthanum, depending on the periodic table you're looking at, cerium and thorium are actually the beginnings of period 6 and 7. It kind of repeats. So we have 1, 2, 3, 4, 5, 6, 7, 6, 7. Just a reminder there. So even though PM, which I believe is praseodymium, is, oh no, it's promethium. Even though promethium is in the 6th period, its final electrons are going to be 4F. It's in the F block, but this is really 4F electrons, and these are 5F electrons. So the F shift happens twice. So if you're working with an F element and looking to hack the periodic table, it's not simply just the period number, it's going to be the period number -2 for F elements. The reason this happens is because the F elements have a lot of electrons, and they, again, rearrange them in order to become more stable. They're going to rearrange their internal electrons, which is why you have kind of this 4s interjected in the middle of the 3s. You have 4d interjected in the middle of the 5s. Then you have 4f interjected in the middle of the 6s. And that's just because electrons would prefer to be in s and p orbitals than they would in d and f orbitals. So anytime an atom gets a chance to rearrange to get s and p electrons as opposed to d and f electrons, it's going to happen. The good thing is that it's a pattern. It's predictable. These F electrons are always going to be shifted such that they're going to be in 4 when they're in the 6th period, and they're going to be in 5F when they're in the 7th period. So even though it sounds like it's not super predictable, it is. Once you learn the rule, it's not so bad. And most of the time, your teachers are not going to have you be writing crazy, crazy electron configurations for these giant elements, but it is important to know how to, because there's always that chance. Plus, it's cool to know. This set of questions is just asking you to find the final chunk of the atom's electron configuration, just to be nice. And here they are. Palladium is going to be 4d8. Palladium is a member, it's number 46 on the periodic table. It's right next to silver. It has 46 electrons in total, even though it's in the 5th energy level. The 5th energy level in the D block is really a 4D, not a 5D, and it's the 8th one over. Francium is in the S block, so there is no reason to do any type of shifting. It is in period 7, and it is the first in that section, so it is an S1. Manganese is in the D block, so remember you have to subtract 1 when you're in the D block, and that is going to be 3D, and because it's the fifth one over, it's 3D5. You can follow that same pattern for any of these other atoms. Here you're asked the opposite to find out what element you're working with based on the final chunk of its configuration. Remember, for S&P electrons, there is no need to shift. You can just take the period number. So antimony, silicon, strontium, and xenon are all pretty predictable. Cadmium is kind of interesting because it is a D block element. So because it's asking us about 4D10, recalling the D shift, it really means we're looking for something in the fifth period. So cadmium is the 10th element in the fifth period of the D block. So I know that that is going to end on 4D10. Yttrium, which is a crazy element, it's number 39. Again, it is in the fifth period. So that is going to correspond to 4D. Because of the D shift, and it is the first element in the D block for that period, so that is why it is 4D1. We can write ground state and excited state electron configurations as well. I know it gets a little bit crazy. Small elements don't usually rearrange their electrons, so their ground state configurations are going to exactly follow the diagonal rule. Some large elements, I alluded to chromium and copper. Even though they will be ground state, they may look like they're excited because they have had the opportunity to rearrange their electrons. Your classroom teacher should talk more to you about that if they are interested in you learning the chromium, copper exceptions to the diagonal rule. But for the most part, anytime a configuration is not following the diagonal rule, it's going to indicate that that atom has been excited and electrons are jumping around. So here we're just looking at a Bohr configuration here, like using principal energy levels. In this case, we have an unfilled energy level. Remember, 8 electrons fit in the third energy level. In total, it would be 3 of them are going to be S electrons and 6 of them are P electrons. But because this is only 7, this is going to indicate that 1 electron jumped out of this level and into the fourth energy level. Anytime we have these sublevels and they're not filled, we can still figure out the atom that it is based on the total number of electrons, because excited electrons or excited atoms in the excited state have the same number of electrons. They're just moved around within the atom. So in this case, we are looking at 1s2, 2s2, 2p4, which is 8 electrons. That makes it oxygen. But in this case, none of them are excited. They're all in the ground state, in their lowest energy state possible. Just looking at the top half here, I can run through and kind of do a check to see that all of this is a ground state configuration. It perfectly matches the diagonal rule, and we are ending on 5p5, which if I hack the periodic table, the fifth period P block, fifth one in, is going to be iodine. And because this perfectly follows the diagonal rule, it is in the ground state. On the other hand, I can look at this configuration: 1s2, 2s2, 2p6, 3s2, 3p4, 4s1. The 3p is not filled. So in this case, I know that I'm absolutely in the excited state. Electrons are not going to jump up to higher energy levels until they fill the lowest ones possible. That's the Aufbau principle. And it is important for us to recognize, using the diagonal rule, the p orbitals hold 6 electrons, and 4 electrons would indicate that it's not filled. So if I go through and I add up all of those superscripts, I would come out with 17, and 17 is going to indicate that I'm working with the element chlorine. One of my 3p electrons has jumped up to the 4s sublevel, which is why there's one missing here and an extra one right there. So that is electron configuration. I would love for you to leave any questions you have in the comment section below the video. Subscribe so you don't miss the next lesson, and I'll see you there. Bye.